Okay, so here we finished part B and then go to part C. Part C, what's new is firstly, we will predict the branch to be not taken, right? Not taken. And then we will have fully bypass. Fully bypass means we can know the branch result like after decode. That is the second stage. Alright, and what's new? Yeah, and the bypass we will also have the ALU result, the executed result can be available from the ALU and the memory register between them, right? And what's new? Oh, and the load, we should wait until the memory, right? We are fetching it from the memory and then try to write it back. So it's available after the memory and write back stage. That is the 4-5. This is the 4-5 stage. This is a 3-4 stage. And what's new? I think that's pretty much all, right? The branch can be the second stage. Yeah, executing and the load. Okay, so let's go through it again. Load with right, fetch, decode, execute, memory, write back. 1, 2, 3, 4, 5. And remember, the load should wait until when? Until the memory and write back line load. So load here, we can make it available. So we are not waiting x1 in a cycle 5. We just make it available after cycle 4. X1 available. And then add. Add also need to read, right? That here is fetch, here is the decode. And here we have the executing here. Yes, because we are using the x1, in the ALU unit, right? So we'll execute here and then go memory, go write back. Yeah, and then the result of the instruction 2 will be available. That means x1 will be available between cycle 5 and 6. Yes, and then we go store. So store still we are doing here, and then here is a store, right? Store, and then we have to waiting for anything. I think not, because we will read the result from x1 between the cycle 5 and 6, and then go to the executable ALU algorithm unit. Yeah, and then memory, and then write back, and here is 8. Yeah, and what's new is the still add. Oh yeah, here is also a RAW, but with the bypass we have saved a lot of time. And that's new. The read is for x2. So x2 nobody want to change it. It just go through smoothly. And then is the sub. Sub we are trying to modify x2 here, right? So x2 will be available after cycle 7. And then we will try to read the x2 for the subtraction, right? And then we can use it just really smoothly in cycle 8, because it is available after cycle 7, right? So x2 can use here, and then we can make what available? Make x4 available, right? We are changing the x4 after cycle 8. And then we go to the branch. Branch here is also a fetch here, and we need to wait for the for the result from the subset, right? So we have to wait, and then we get the result, and then we can decode. And decode the result for the branch can be available after the decode because the bypass. So here you can see the address or the branch result, no matter what you want, just the result after for the branch. Okay, so will be available after cycle 9. So and we are predicting to be not taken, but is it correct? No, because we will take for 98 iteration, and just not take for the last, right? We will take for 98 cycles, 98 iterations. So it's mispredicting. So if the branch, the next instruction, let's say I+1, it should fetch an instruction from the address, right? No matter what happened. So it's wrong. Let's say the address ADD1, ADDR1, and here the address 2, ADDR2 is not the same. So here is a wrong. So what's wrong? If we have a wrong, then we will go a flush, and then we will go to the I+2, or you can say it's the loop +1 with the another load, right? Another load will be start just right after the cycle 9, right? Because we get the address, and we can give the address here for the instruction fetch. Yeah, and then we will do the same thing, the decode, execute, memory, and write back. So you can see for each loop, actually, we will just take 9 cycles, right? So do the same thing, 9 multiplied by 98, and the last one. And the last one will take a full cycle, that is 12. And that is 894, sorry. Yeah. That's for part C. And how about part D? Part D is actually doing nearly the same thing. So still bypass, still ALU will available and load available, and the branch have the result. The only thing different is that we are predicted to be taken. So we are correct, right? Correct for our 98 iteration, only wrong for the last one. So based on the analysis above, we can still do it again, right? Load, add, store, add. Let's go this for first. Oops. Yeah. Fetch, decode, execute, memory, write back. 1, 2, 3, 4, 5. Yes. And then the only thing will affect is the branch stage, the branch instruction, right? So everything will be the same above. Store, oops, yeah, decode, get the thing, read here, right? Read here, and memory, and store, and then fetch, decode, execute, memory, right there. Sub is here, fetch, decode, execute, x4 available, right? And memory, and write back. So how many you take? 6, 7, 8, 9, 10. And okay, here we comes with the branch. Okay, still here, fetching here. We have to wait for the result of the x4. Oh, here is x2, sorry. Here is x4. Okay, wait for a cycle, and then we get what we want to be decoded, and the decode result, that's still using the address 2, and then execute memory right back. 11, 12, right, and the address result will be here, and the I plus 1 we will try to fetch from the cycle 9, and here we can still using the address 1 to compare is it correct with address 2. But since we are predicted correctly, right, we are predicted correctly, so the address we are predicting is correct, so we can just go with the next step, right? The next step is the decode, right? The next is the decode, execute, memory, right back. And here will just be our loop plus 1, the new load, the new load instruction. So because we are correctly predict, we are predicted to be taken, and actually it is taken. So these two addresses will be the same. That means the decode can go through smoothly, successfully, right? So yeah. And so how about one loop? So you can see here is the new loop, right? So the one loop will stop or finish in cycle 8. So that's 8 multiplied by 98 and plus a full for the last loop, yeah, plus 12. So that is 796. Well, so this is how you calculate and evaluate, just because the prediction, you predict it to be taken and it is correct, so the address is correct. So maybe you will talk about how about the last iteration. So because the last iteration we will stop, we will not going through the 100 iteration, right? So it's no need to be another comparison. Okay. And if here we are, what we did, here we are predicted to be not taken, right? Not taken, and it's mispredict. So mispredict, that means here will be the wrong address. Address 1 will be wrong compared with address 2. Address 2 will say, okay, I will take it. I will take, but in the instruction 1 says I will not take. Not take means I will do something new, right? Such as I will do another instruction like multiple something. So that is out of our loop. So let's say, yeah, in multiple here, is it correct? No, the instruction for multiple we are fetching is incorrect compared with what we want. We want to be the loop to be a new load, right? The load, not a multiple. So we have to fetch the loop, the instruction for the next loop load again. So here makes a wrong predict. Here makes a correct predict. Yeah, if we making the correct predict, then everything goes fine. So yeah, because we are predicted to be taken, will be taken. So here will be the next loop, a next load address, and it's correctly the same for the result after our decoding, or for the branch stage, branch instruction. I think this will help you go through and understand what happened for the pipeline and the branches. Thank you.